I have some circles today and they're made of brass, and the wonderful thing about circles, as we all know, is they roll, which is why as an invention they're up there just behind fire and ahead of sliced bread. So if I set this going, in theory, look at that, right, rolls right across the table. And the reason a circle rolls, and sorry if I'm breaking this down a bit too much, is because as it moves, its center of mass, so if I draw that over here, not bad. Funny I had a template I could have drawn around. As a circle rolls, its center of mass stays at that same height, which is why if I tried to roll a square, I've got a square here, and there's its center of mass in the middle. As it rolls, the center of mass has to go up, and then it goes down, right? And so up and then down. So it will roll, but you've got to drive it. You've got to be constantly forcing it, because when it's here, its center of mass is there. But then if it lifts up, the center of mass has gone up. So that will stay the same. Whereas as you turn a square, the center of mass has to be raised. The thing about a circle is you still have to drive it because you've got friction and, you know, as always, we live in a messy physical reality, but the actual center of mass doesn't go up or down, so that means it rolls quite neatly. It's not the only way you can roll a circle so its center of mass stays at the same height. I've got two circles here, and they've both got notches cut into them, and that means I can slot them together. Now they are brass and they really grip quite. Let me just make sure I got that right in. So I've now got two firmly locked together circles, and they're at right angles, they're orthogonal to each other. And if I put them down, the center of mass is kind of, well, probably there-ish, and it's a certain height above the table. The amazing thing is, as it rolls, that center of mass stays at exactly the same height. Look at that. The center of mass of each individual circle, because circles are quite predictable, it's in the middle. Actually, I've got some cardboard ones, right? So the center of mass, we can draw it on. In fact, it's got a picture of the discs on the disc, which I find hugely entertaining. So that's the center of the mass is there in the middle of that. That kind of makes sense because it's, you know, the same distance away. That's the, you know, symmetric center of that circle. When you got two of them together, it gets a bit more complicated. And so now you think, well, where's the exact center of this? And you can calculate it, which I did just to be thorough, or you can just say, look, symmetrically, that is the point there, that point right in there is the kind of symmetric point, right in the center of all the mass, which is why we give it the strange name, the center of mass. And so as long as that spot stays the same height above the surface, this nice flat table, then you're not adding or receiving or taking out any potential energy as it rolls. So that's why if this is just the right intersection and that dot stays the same height above the table, that's why you get the rolling effect. There we go. If you want to make these yourself, then you'll see I made them by cutting a notch into a piece. So cards easier. You can make them out of CDs or anything else. These are made of brass. So they roll a bit nicer, but they're a bit harder to machine up. But if you want to make some of these yourself, you want to make that cut and you want to work out how far in you have to cut for the whole thing to work. And you can calculate mathematically what you have to do. In fact, the easiest way to do the maths, which is of course why we're here, is to consider when you put them together, the center of this disc, so that's the exact middle of that disc there, that's the middle of that disc there. Normally that'd be, if we didn't have grooves in them, they would sit like that. And so that's the radius of this disc. That's the radius of this disc. And so the centers would be 2 times the radius apart at all times. By having those slots though, they get closer together. And the question is, how far apart are these two centers now that we've put the slots in there so that height doesn't change? And we can work that out with some triangles. So here we go. Now, there are 2 important states we have to worry about with the wobbler disc. And one is when you're looking at it perfectly end on and they're both 45 degrees to the surface. So that's that position there, which I'm going to draw end on here. There. So that's you know, looking at it that way, straight down. So the center of mass is there. It is now, we're going to call this the height above the table. That there is the radius of the discs, and that there is 45 degrees, or pi on 2, depending on what you want to say. I mean, you could say that is tau on 4, but then you'd be an idiot. So because that's 45, it means this here is also the same as the height, because we have a wonderful 45-45 right angle triangle there. And so we know, using our friend Pythagoras, that r squared equals h squared plus h squared, which equals 2h squared. And so if we take a square root of that, we know the radius equals square root of 2 times h. So that's our ratio in that position. The important thing is we want that h to stay exactly the same height even when it's rolling. So once it's rolled for a bit and it ends up in that position, so now you've got one disc coming straight up and the other one is pretty much, well, it's not flat, but you know what I mean there. So let's sketch that. So we got one disc like that, and then there's the center. Now that center is going to line down to the surface, and there's going to be the other disc there, like that. Okay, so that's in that position. So once again, there's the center of that disc there, there's the center of that disc there. What we want to calculate is this distance that the centers are apart. So that's d, the distance we want to know, because that tells us how big to make the notches so that they sit at the right distance. And that d we can calculate because we know that's the center down to where it touches. That must be the radius of that disc. And this here, that height there must be the radius because it's the circle standing straight up. The center of mass is there, which is halfway between the two centers. And that is the h, which is all important. And that distance there, from that center to there, well, that's half of this. So that little distance there, that's d on 2, because it's half of that distance. And so now we can use our good friend similar triangles, which means that for this small triangle here, so to get from the bottom to there, that's r plus d on 2 divided by h equals the big triangle, which is r plus d over r. Right, and so now we're off and racing. All we have to do is solve this to work out what d is. We want to get rid of that annoying h there, but we know from over here that h equals r divided by root 2. So we can substitute that in over here. So that now becomes r plus d on 2 over r over root 2, and that still equals r plus d over r. To tidy this up a little bit, I'm going to multiply both sides by r, because it's going to cancel out with these ones underneath. And so that ends up being root 2 outside of r plus d on 2 equals r plus d. And to get rid of this mess out the front here, I'm going to multiply both sides by root 2. So if I multiply this by root 2, I get a 2 out the front. So that becomes 2r plus d, because that 2 cancels with the half. And if I multiply this by root 2, I get root 2r plus root 2d. And now I can put all the same terms on the same side. So this one over here, if I subtract that root 2 d from both sides, I get 1d minus the root 2 outside of d equals, and I subtract the 2r from both sides, that's going to be root 2 minus 2r. Have I made any mistake? I've probably made a mistake in there somewhere. So all we want to do now is work out the ratio that d is compared to the radius. And so all we have to do is rearrange this to get d in terms of r. And because I know where we're going, and because I'm picking a very careful path through the algebraic field we could be working our way across, I mean, if you try this, if you set up different triangles, or you did all these steps differently, you'd still get the same answer at the end, because that's why maths is wonderful. Multiply both sides by 1 plus root 2. 1 times 1 is 1, and so we're going to multiply that by that as well. Negative 2 times 1 is going to be minus 2, so they've cancelled out, that's lovely. And so all of this is showing us that the wobbling discs work only when those two centers are root 2 times the radius of the discs apart. There are far more complicated ways through this terrain, but no matter what you do, no matter what algebra you're dancing around with, as long as you're careful, everything drops out at the very end. It's so lovely. No matter what you do, everything settles and cancels out, and you always end up with root 2 times the radius. And I love the fact that it's quite a complicated system, and a decent amount of maths to get there is such a nice, simple, neat answer. And that for me is mathematics. First time I did this, I didn't work out that distance between the centers. I worked out, because I'm a pragmatic man at heart, actually I won't pull those apart because they're really wedged in. As a pragmatic man, I worked out what is that distance there. So I did that calculation to try and calculate that. And you can work it out now. Either you can work backwards from this, or I can just ruin the surprise and tell you that that distance there is 1 minus 1 over root 2 times the radius. So in fact, if you want to make one of these, and for once I will actually sketch one properly. So there's your disk, and that's got some radius r. That distance there is 1 minus 1 over root 2 times whatever that radius r is. If you're a lazy person, that is about 29%. That is 0.29 times the radius, give or take.
29%.
29%. It's about a third. But if you want it to work really well, then you need to go for 0.29 times the radius, or you can work it out.
If you want to hear and see even more mathematics from Matt Parker, more than we could ever fit in 100 Numberphile videos, he's got a new book out, Things to Make and Do in the Fourth Dimension. Here are the front covers of the book in the UK and the United States. You can already order it from wherever you normally get books, or if you want a copy hand-signed by Matt himself, go to his website, and I'm going to put the links in the video description. I think if you get the one signed by Matt, you're going to get the UK one no matter where you live. Check it out. People like Matt give loads of time to Numberphile. We filmed this video on a Sunday afternoon when he could have been out with family and friends. There's not much we can do in return, but checking out his book is one of those things. And don't do it just to be nice, do it because it's an excellent book and worth reading.